Tonight, we're going to explore one of the strangest contradictions in all of physics. A black hole can spin. Not like a planet, not like a ball. It warps the fabric of space-time itself into a swirling vortex so powerful that even empty space gets dragged along. And here's where it gets truly bizarre. There's a speed limit. A boundary written into the mathematics of the universe that says a black hole can only spin so fast. Push it to that edge, and the equations predict something terrifying. The event horizon, the one thing that keeps the singularity hidden from the rest of the universe, begins to vanish. What lies beyond that limit isn't just a faster black hole. It might be something the universe was never supposed to reveal. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Here's what most people picture when they hear that a black hole spins. They imagine something solid, something dark and spherical, rotating on an axis the way Earth rotates on its axis. A massive ball of compressed matter twirling through space. And that picture feels intuitive because everything in our experience that spins has a surface. A basketball has a surface. A planet has a surface. A figure skater has a body you can see rotating. But a black hole doesn't have a surface. There's nothing solid there. No rock, no metal, no crust, no material edge carving through the void. A black hole is a region of space-time so severely warped by gravity that nothing, not light, not matter, not information of any kind, can escape from within its boundary. That boundary, the event horizon, is not a wall or a shell you could touch or stand on. It is a mathematical surface, a threshold defined entirely by the geometry of space-time itself. Think of it less like the surface of a planet and more like a point of no return in a river. Imagine a river flowing toward a waterfall. Somewhere upstream, there's a line past which the current is so strong that no fish, no matter how powerful, can swim back. That line is real, but it's not a wall. It's a threshold defined by the behavior of the flow. The event horizon works similarly. It's the point where gravity becomes so extreme that even light cannot climb back out. You could pass through it without touching anything, because there is no surface to hit. So when physicists say a black hole spins, they don't mean some object is rotating the way a planet rotates. They mean something far stranger. They mean the geometry of space-time around the black hole is twisted. The warping itself carries a kind of rotation. Space-time near a spinning black hole doesn't just curve inward toward the singularity. It also swirls, dragging everything along with it. Not just matter, not just light. Even empty space itself gets caught in this rotation, pulled along by the spinning geometry. The spin is not in any material. The spin is in the fabric of reality. This distinction is critical because it changes what the word spin even means. For a normal object, spin is straightforward. Earth rotates on its axis once every 24 hours. You can measure this by tracking a point on the equator and watching how fast it moves. A point on Earth's equator moves at about 1,040 miles per hour. That's a concrete number tied to a physical surface moving through space. There's a real, tangible surface, and that surface has a measurable velocity at its edge. But a black hole doesn't have an edge. The event horizon is not a material boundary. It's a region in space-time where the escape velocity exceeds the speed of light. You cannot assign an ordinary rotational speed to the event horizon the way you can assign one to Earth's equator, because the event horizon is not a physical surface moving through space. It's a geometric feature of the space-time itself. It doesn't rotate through space. Space rotates around it. So how do you describe the spin of something that has no surface? How do you measure the rotation of something with no edge? The answer is angular momentum. In physics, angular momentum is the rotational equivalent of regular momentum. Just as a moving object has momentum proportional to its mass and velocity, a spinning object has angular momentum that depends on its mass and how its rotation is distributed. Angular momentum is one of the most fundamental conserved quantities in the universe. It doesn't appear from nowhere or vanish into nothing. If something has angular momentum, it keeps it unless it transfers that angular momentum to something else. This law is as ironclad as the conservation of energy, applying to everything from spinning atoms to orbiting planets to collapsing stars. A black hole carries angular momentum, even though it has no solid body. That angular momentum is encoded in the geometry of space-time itself. It's woven into the fabric of how space and time curve and twist near the black hole. The more angular momentum a black hole has, the more intensely space-time swirls around it. Physicists describe the spin of a black hole using what's called a dimensionless spin parameter. This is a single number that compares the black hole's angular momentum to its mass. You can think of it as a ratio. How much rotation does this black hole carry relative to how heavy it is? The scale runs from 0 to 1. A value of 0 means no spin at all. The black hole is perfectly still, with space-time curving inward symmetrically in all directions. A value of 1 means maximum spin. The black hole is rotating as fast as the mathematics of general relativity will allow. No fractions, no complicated units, just a clean number between 0 and 1 that captures everything about how fast a black hole is spinning. And that ceiling at 1 is where things get truly unsettling. Because the mathematics doesn't just say the spin parameter can go up to 1, it says something happens at 1. The structure of the event horizon changes. And beyond 1, if such a thing were even possible, the equations describe something that might not be a black hole at all. We'll get there. But first, we need to understand where all this angular momentum comes from. If black holes are just regions of warped space-time, how do they end up spinning in the first place? The answer begins with how black holes are born. Most stellar mass black holes form from the deaths of massive stars. When a star much larger than our Sun, typically at least 20 to 25 times its mass, exhausts the nuclear fuel in its core, disaster follows. For millions of years, nuclear fusion pushed outward, balancing the crushing force of gravity. When the fuel runs out, that balance collapses in an instant. The core implodes. If it is massive enough, nothing can stop the collapse. Not the quantum pressure of electrons, not the repulsive force between neutrons. The matter falls inward past every known physical limit, creating a singularity and an event horizon around it. Now here's the key. The star that created the black hole was already spinning. All stars rotate. Our Sun completes one rotation about every 25 days at its equator. Some stars spin much faster. Young, massive stars can rotate at hundreds of miles per second at their surfaces. And when the core of such a star collapses, it doesn't lose its angular momentum. Angular momentum is conserved. It is one of the most fundamental laws in physics. As the core shrinks from something the size of a small planet to something smaller than a city, all that angular momentum gets concentrated into a dramatically smaller volume. You've seen this principle in action even if you didn't realize it. Think of an ice skater performing a spin. When she extends her arms, she rotates slowly. When she pulls her arms tight against her body, she spins faster, much faster, Her angular momentum stays the same, but because her mass is now distributed closer to her axis of rotation, the spin rate increases dramatically. It's not magic, it's conservation of angular momentum. The same angular momentum in a smaller space means faster rotation. The same thing happens when a stellar core collapses. The original star might have been rotating relatively slowly, one complete turn every few weeks. But when that core compresses down to the scale of a black hole, the spin rate increases enormously. The angular momentum is preserved, packed into a fantastically smaller structure. The resulting black hole is born already spinning, sometimes spinning very rapidly, carrying the angular momentum of the collapsing stellar core with it into its new existence as a region of twisted space-time. But birth is not the only way black holes gain angular momentum. The second major source is accretion. This is the process by which a black hole feeds, pulling in matter from its surroundings. In many astrophysical situations, a black hole doesn't sit alone in empty space. It might orbit closely with a companion star, whose outer layers it strips away with its gravity. Or it might sit at the center of a galaxy, surrounded by vast clouds of gas and dust slowly spiraling inward over millions of years. This infalling matter almost never falls straight in. In nearly every real situation, it has some sideways motion relative to the black hole. Maybe the companion star was orbiting and the gas it shed carries that orbital velocity. Maybe the gas cloud was already rotating slowly before the black hole began pulling it inward. Whatever the reason, the infalling matter carries angular momentum of its own. It doesn't plunge directly into the event horizon. Instead, it forms an accretion disk, a flattened, swirling structure that orbits the black hole like a vast whirlpool. The matter spirals inward through this disk, slowly losing energy through friction and radiation, getting hotter and brighter as it falls deeper into the gravitational well, moving closer and closer to the event horizon, until finally it crosses that threshold and disappears. When matter crosses the event horizon, it adds its angular momentum to the black hole. If the matter was orbiting in the same direction the black hole was already spinning, it adds to the spin. The black hole speeds up. If the matter happened to be orbiting in the opposite direction, it subtracts from the spin. The black hole slows down. But in most astrophysical situations, the accretion disk forms in a consistent direction, and the matter falling in preferentially adds angular momentum in one direction over millions or billions of years. Over cosmic timescales, this accumulates. Each bit of infalling matter adds a small increment of angular momentum. Like drops of water filling a bucket, the spin builds up gradually but relentlessly. The black hole rotates faster and faster, inching closer and closer to that theoretical maximum. And as we'll see, the closer it gets to that limit, the more extraordinary the consequences become. The effects on the surrounding space-time are not subtle. They reshape everything around the black hole, changing how matter orbits, how light bends, and how energy can be extracted from the region near the event horizon. But there is a third way black holes gain angular momentum, and it is perhaps the most violent: mergers. When two black holes orbit each other and eventually collide, the angular momentum of the original binary, the orbital energy of the two black holes circling each other at tremendous speed, gets converted into the spin of the final merged black hole. These mergers are among the most energetic events in the known universe. In the final moments before two black holes merge, they spiral toward each other at a significant fraction of the speed of light. They orbit each other hundreds of times per second, moving faster and faster as they draw closer and closer. The gravitational waves they produce carry enormous energy, rippling outward through the fabric of space-time itself at the speed of light. When the two black holes finally merge, the resulting single black hole is born with angular momentum determined by a complicated combination of the two original spins and the orbital angular momentum of the pair. We have actually detected these mergers. In 2015, the LIGO Observatory made the first direct detection of gravitational waves from two black holes merging roughly 1.3 billion light years away. The two black holes, approximately 29 and 36 times the mass of our Sun, spiraled together and merged into a single black hole of about 62 solar masses. The missing 3 solar masses were not lost. That mass was converted into pure energy and radiated away as gravitational waves in a fraction of a second. For a brief moment, that single merger was radiating more energy per second than all the stars in the observable universe combined. More than every star in every galaxy in every corner of the cosmos, all outshone by two black holes crashing together in a region smaller than the width of the Atlantic Ocean. The resulting black hole was born spinning. Analysis of the gravitational wave signal allowed physicists to estimate the final spin parameter, and it came out to roughly 0.67 of the maximum. A single merger can create a rapidly spinning black hole almost instantly, in contrast to the slow, steady spin-up of accretion that unfolds over millions of years. Since that first detection, LIGO and its partner observatories have detected dozens of black hole mergers. Each one tells us something about how angular momentum is shared and redistributed when black holes combine. Some mergers produce slowly spinning remnants. Others produce rapidly spinning ones. The outcome depends on how the original black holes were spinning relative to each other and relative to their orbit. Now, to truly understand what spin does to a black hole, we need to talk about the mathematics, and that means we need to talk about two landmark solutions to Einstein's field equations of general relativity. The first came in 1916, just 1 year after Einstein published his revolutionary theory. A German physicist named Karl Schwarzschild, serving on the Russian front during the First World War, found an exact solution to Einstein's field equations describing the spacetime around a perfectly spherical, non-rotating mass. This was remarkable because Einstein himself hadn't believed exact solutions would be found so quickly. The Schwarzschild solution describes the simplest possible black hole. No spin, no electric charge, just mass. A perfectly symmetric gravitational field curving space-time inward toward a central singularity, surrounded by an event horizon at a precise radius determined solely by the mass. The Schwarzschild solution was elegant and groundbreaking. It predicted the existence of what we now call black holes, though that term would not be coined for another 5 decades. It showed that if enough mass is compressed into a small enough region, an event horizon inevitably forms, a boundary from which nothing can escape. But the Schwarzschild solution has a significant limitation. It describes only a non-rotating black hole. And as we have discussed, real black holes almost certainly spin. The matter that formed them was already spinning. The accretion that feeds them adds spin. The mergers that create some of them generate spin. A perfectly non-rotating black hole would be an extraordinary exception, not the rule. For nearly 50 years after the Schwarzschild solution, physicists struggled to find a corresponding solution for a rotating black hole. The mathematics is extraordinarily difficult. Einstein's field equations are a set of 10 coupled nonlinear partial differential equations. Solving them exactly for even simple cases is a monumental achievement. Adding rotation makes the problem drastically harder because rotation breaks the perfect spherical symmetry of the non-rotating case. A spinning black hole is not the same in all directions. It has a preferred axis, the axis of rotation, and the space-time around it behaves differently at the equator than at the poles. Every attempt to solve the equations for this more complex situation ran into walls of mathematical complexity. Then, in 1963, a New Zealand mathematician named Roy Kerr achieved what many had considered impossible. He found an exact solution to Einstein's field equations for a rotating black hole. The Kerr solution, as it is now known, is considered one of the most important results in all of theoretical physics. It describes the complete space-time geometry around a black hole that spins, and it reveals consequences that the non-spinning Schwarzschild solution never hinted at. The Kerr solution is described by just two numbers: mass and angular momentum. That's all. Those two quantities alone determine everything about the space-time around a rotating black hole: how it curves, how it twists, where the event horizon sits, how light and matter behave in its vicinity. This extraordinary simplicity is captured in a famous observation by the physicist John Wheeler, who said that black holes have no hair. What he meant is that no matter how complicated the star was that formed the black hole, no matter what elements it was made of, no matter what its temperature or magnetic field or internal structure, the resulting black hole is completely described by at most three quantities: its mass, its angular momentum, and its electric charge. In practice, astrophysical black holes are expected to carry negligible charge because they rapidly attract and absorb oppositely charged particles from their surroundings, neutralizing almost instantly. This is why the Kerr solution, which describes a rotating black hole with zero charge, is the one that matters for real black holes in the universe. All the other details of the original star are swallowed behind the event horizon, lost to the outside universe forever. What Kerr discovered was that a spinning black hole is fundamentally different from a non-spinning one. Not just slightly different, not just a minor tweak, qualitatively, structurally, profoundly different. The geometry of space-time transforms in ways that have no parallel in the non-rotating case. A non-rotating Schwarzschild black hole has a single event horizon. A rotating Kerr black hole has two, an outer horizon and an inner one. A non-rotating black hole has perfect spherical symmetry. A rotating black hole is flattened at the poles and wider at the equator, its horizon squashed by the effects of spin. A non-rotating black hole simply curves space-time inward. A rotating black hole curves space-time inward and twists it sideways, dragging matter, light, and even the vacuum of empty space along with its rotation, in a phenomenon so strange it had to be given its own name. These differences are not just mathematical curiosities, they have real, measurable physical consequences. They affect how accretion disks glow, how jets of matter are launched, how energy can be extracted from the black hole's environment, and whether there exists a limit on how fast a black hole can spin. And it is that last question, the question of the limit, that sits at the heart of everything we are exploring tonight. Because the Kerr solution reveals something remarkable. As you increase the spin parameter from 0 toward 1, the geometry of spacetime changes smoothly and continuously. The effects become more dramatic, more extreme, but they remain well behaved. The mathematics holds together. The event horizon shrinks. The twisting of spacetime intensifies. The region where these extreme effects dominate grows larger, but at a spin parameter of exactly 1, something qualitatively different happens. The two horizons converge, and beyond 1, if such a value could ever be reached, the solution describes something that may not be a black hole at all. This is where physics encounters one of its most fascinating and troubling boundaries. Not a boundary in space, but a boundary in what the universe appears to permit. Every black hole in the universe acquired its spin through some combination of these three mechanisms: collapse, accretion, and mergers. Some were born spinning rapidly from the implosion of massive rotating stars, carrying the compressed angular momentum of the original stellar core. Some were spun up slowly over millions or billions of years by the steady consumption of orbiting matter, each infalling particle adding its own small contribution. Some received their angular momentum all at once in a single, catastrophic merger lasting less than a second, and many experienced all three at different stages of their existence. A black hole might be born from collapse with moderate spin, then accrete matter for 1 billion years, gradually increasing its rotation, and then merge with another black hole, dramatically reshaping its angular momentum in a violent instant. The result is that the universe contains black holes across a wide range of spins. Some rotate slowly with spin parameters of perhaps 0.1 or 0.2, barely twisting the spacetime around them. Others spin much faster, approaching 0.9 or even higher, creating intense vortices in the fabric of spacetime. And the faster they spin, the more extreme the effects become, the more dramatic the phenomena in their vicinity, and the closer they press against that mysterious boundary that the mathematics says they cannot cross. What that boundary is, what happens near it, and why the universe seems to enforce it, that is what comes next. Because when a black hole spins fast enough, the very structure of space-time around it transforms into something that challenges our deepest understanding of gravity, geometry, and the nature of reality itself. We've established that black holes spin, that their rotation is not the turning of a surface, but a distortion woven into the geometry of space-time itself, and that angular momentum accumulates through stellar collapse, through the slow feeding of accretion, and through the violent collisions of mergers. But we haven't yet confronted what that spin actually does to the surrounding universe. Because a spinning black hole doesn't simply carry angular momentum the way a bank carries money, storing it passively behind a vault door. It actively reshapes its environment. The space-time near a rapidly spinning black hole behaves in ways that have no parallel in your everyday experience. The intuitions you've built from living on a planet with gentle gravity and slow rotation are not just inadequate here, they are wrong. The most striking consequence of black hole spin is a phenomenon called frame dragging, and frame dragging is exactly what it sounds like. The rotation of the black hole literally drags the fabric of space-time along with it. Imagine plunging a spoon into a jar of thick honey and twisting it. The honey closest to the spoon gets pulled along, swirling in the same direction the spoon is turning. Farther from the spoon, the effect weakens. The honey near the edges of the jar barely moves. Now imagine the honey is space-time itself. That's frame dragging. A spinning black hole twists the space-time near it, forcing everything in that region, matter, light, radiation, even empty vacuum, to rotate in the same direction as the black holes spin. Not because some force is pushing these things sideways, but because the space and time they exist in is itself being dragged around. This isn't science fiction. This isn't even purely theoretical. Frame dragging was predicted in 1918 by two physicists, Josef Lenz and Hans Thirring, who worked out the consequences of Einstein's general relativity for a rotating massive body. They showed that a spinning object doesn't just curve space-time inward the way a non-spinning mass does. It also twists space-time sideways, pulling it along with the rotation. This effect came to be known as the Lenz-Thirring effect, and it applies to any rotating mass, not just black holes. Even Earth produces frame dragging. Earth is spinning, and the rotation drags the space-time around our planet by a tiny, almost imperceptible amount. In 2004, NASA launched a spacecraft called Gravity Probe B specifically to measure this effect. The spacecraft carried 4 ultra-precise gyroscopes into orbit. If space-time were perfectly static, those gyroscopes would always point in the same direction. But if the rotation was dragging space-time along, they would slowly tilt. And that's exactly what happened. After more than a year of data collection and years of careful analysis, the results confirmed that Earth's rotation does indeed drag space-time. The measured drift matched Einstein's predictions. Frame dragging is real. It has been measured. It is not a hypothesis or a theoretical curiosity. It is a confirmed fact about how the universe works. But here's the thing. Earth's frame dragging is almost immeasurably small. Earth is not very massive and it rotates slowly. The effect amounts to a drift of about 0.039 arcseconds per year. A measurement so tiny it required some of the most sensitive instruments ever constructed. You'd never notice it in everyday life. No human has ever felt the effects of Earth's frame dragging. It takes incredibly precise instruments to detect it at all. Near a spinning black hole, frame dragging is not subtle. It is overwhelming. A stellar mass black hole might contain 10 or 20 times the mass of our Sun compressed into a region smaller than a city, and it might be spinning at a significant fraction of the theoretical maximum. The frame dragging near such an object doesn't gently tilt a gyroscope by a fraction of a degree per year. It seizes space-time and hauls it around, creating a vortex so powerful that nothing nearby can resist it. The closer you get to the black hole, the stronger the dragging becomes, and at a certain distance, something extraordinary happens. The dragging becomes so intense that space-time itself is moving faster than any object could travel in the opposite direction. This brings us to one of the most remarkable features of a spinning black hole: the ergosphere. The ergosphere is a region outside the event horizon. Let me emphasize that. Outside the event horizon. You can enter the ergosphere and still escape. You haven't crossed the point of no return. The event horizon is still somewhere deeper, closer to the singularity. The ergosphere surrounds it like a shell, extending outward into space beyond the horizon's boundary. But the ergosphere is not ordinary space. Inside the ergosphere, frame dragging is so extreme that standing still becomes physically impossible. Not difficult, not impractical, impossible. There is no amount of thrust, no engine, no rocket, no force in the universe that could keep you stationary within the ergosphere. You will be dragged along with the black hole's rotation, whether you like it or not. Even if you fired the most powerful engines imaginable in the direction opposite to the spin, you would still be carried forward. The space-time you exist in is moving. You can move within it. You can aim your ship in different directions within that rotating space-time. But relative to the distant stars, relative to the universe outside the ergosphere, you are rotating around the black hole. You have no choice. Think of it like standing on a conveyor belt, moving faster than you can walk backward. You can walk in any direction on the belt, even backward. But relative to the floor, you're always moving in the direction the belt is going, because the belt is faster than your legs. The ergosphere is like that, except the conveyor belt is space-time itself, and faster than your legs becomes faster than anything in the universe, including light. The shape of the ergosphere is not a perfect sphere. It's flattened, extending farther from the event horizon at the equator than at the poles. At the poles, the ergosphere barely extends beyond the horizon. At the equator, it can reach out to roughly twice the horizon's radius, depending on how fast the black hole is spinning. The faster the spin, the larger the ergosphere becomes. A slowly spinning black hole has a thin, barely noticeable ergosphere. A rapidly spinning one has a large, dramatic ergosphere extending well beyond its horizon. This asymmetry exists because frame dragging is strongest at the equator. Just as Earth's rotation is fastest at the equator and zero at the poles, a spinning black hole's frame dragging is most intense in the equatorial plane and weakest along the spin axis. So the ergosphere bulges outward at the equator, where the dragging is fiercest. The ergosphere is important for reasons we'll discuss shortly, because it creates a region where energy can be extracted from the black hole's rotation. But first, let's look at what spin does to the event horizon itself. We mentioned in our earlier discussion that a non-spinning Schwarzschild black hole has a single event horizon, a perfectly spherical boundary whose size depends only on the black hole's mass. A spinning Kerr black hole is different. It has two horizons, an outer event horizon and an inner event horizon, sometimes called the Cauchy horizon. The outer horizon is the one you'd encounter first if you fell toward the black hole. It functions the way you would expect. It's the point of no return. Once you cross it, you cannot escape. The inner horizon sits deeper inside, closer to the singularity, and its physics are far more exotic and uncertain. What matters for our discussion is what happens to these two horizons as the spin increases. When the spin parameter is 0, there is only one horizon, the Schwarzschild horizon. As soon as the black hole begins to spin, even slightly, this single horizon splits into two. The outer horizon sits at a radius slightly smaller than where the Schwarzschild horizon was, and the inner horizon appears at a much smaller radius, deep inside. As the spin increases, the outer horizon shrinks, and the inner horizon grows. The gap between them narrows. The faster the spin, the more compact the outer horizon becomes relative to the black hole's mass. This compactness has consequences that go far beyond geometry. It opens up a region of space-time that will be hidden inside the horizon of a non-spinning black hole, a region now accessible to orbiting matter. And that changes where the closest stable orbit can exist, which in turn changes everything about how the black hole interacts with the universe around it. The full significance of what happens when those two horizons finally converge, when the gap between them closes entirely, is something we'll confront later. For now, what matters is this. A spinning black hole has a more compact throat than a non-spinning one of the same mass, and that compactness unlocks extraordinary physics. This brings us to one of the most consequential differences between a slowly spinning and a rapidly spinning black hole: the innermost stable circular orbit. In any gravitational field, there are orbits. The moon orbits Earth, Earth orbits the sun, stars orbit the centers of their galaxies. Near a black hole, matter in an accretion disk orbits the black hole, spiraling inward through a series of progressively smaller orbits. But there's a limit. Below a certain radius, no stable circular orbit exists. If matter drops inside that boundary, it doesn't spiral anymore. It plunges. It falls directly into the black hole in a final, irreversible dive. For a non-spinning Schwarzschild black hole, this innermost stable orbit sits at a distance of about 3 times the event horizon's radius. That's the closest any object can orbit without inevitably spiraling in. Any closer, and the orbital mechanics become unstable. Small perturbations grow rather than damp out. An object nudged slightly inward doesn't oscillate back to its orbit. It falls. Think of it like the edge of a cliff. You can stand safely at a distance, you can even lean toward the edge, but past a certain point, you lose your footing and there's no recovering. For a spinning black hole, this boundary changes dramatically. If matter orbits in the same direction as the black hole's spin, riding along with the rotation, the innermost stable orbit shrinks. It moves closer to the event horizon. The faster the black hole spins, the closer this orbit gets. At the theoretical maximum spin, the innermost stable orbit for matter orbiting with the spin essentially touches the event horizon itself. The closest stable orbit is right at the boundary of no return. This has enormous consequences for energy. When matter spirals inward through an accretion disk, it releases energy. Gravitational potential energy is converted into kinetic energy and thermal energy. The gas heats up. It glows. It radiates. The closer the matter can orbit before taking its final plunge, the more energy it releases along the way. The innermost stable orbit acts as a kind of launching ramp. Matter that reaches this orbit has already surrendered as much energy as it's going to give up through orbital mechanics. After this point, it plunges in, and whatever energy it still carries vanishes behind the event horizon, lost to the outside universe forever. For a non-spinning black hole, the energy released by matter falling from a far away to the innermost stable orbit amounts to about 5.7% of the matter's rest mass energy. That 5.7% gets radiated away as light and heat. Now, 5.7% might not sound impressive, but compare it to nuclear fusion, the process that powers our sun. Nuclear fusion converts only about 0.7% of rest mass into energy. Accretion onto a non-spinning black hole is already about 8 times more efficient than the most powerful energy source known in everyday astrophysics. But for a rapidly spinning black hole, where the innermost orbit moves much closer to the horizon, the efficiency skyrockets. At the maximum theoretical spin, up to about 42% of the infalling matter's rest mass energy can be released before the matter crosses the event horizon. 42%. That's roughly 60 times more efficient than nuclear fusion. It means that a spinning black hole can extract nearly half of the total energy contained in everything that falls into it, and radiate that energy outward before the matter disappears forever. This is why rapidly spinning black holes power some of the most luminous objects in the universe. The extraordinary efficiency of energy extraction near a fast-spinning black hole is what makes certain phenomena even possible. And that brings us to how spin allows energy to be extracted directly from a black hole itself. Not just from the infalling matter, but from the rotational energy stored in the twisted space-time around the black hole. In 1969, the British mathematician Roger Penrose proposed an elegant thought experiment. Imagine sending an object into the ergosphere, that region outside the event horizon, where space-time is being dragged along with the black hole's rotation. Inside the ergosphere, something strange happens to the definition of energy. Because space-time is being hauled around, certain trajectories that would normally be impossible become available. Specifically, it becomes possible for an object to split into two pieces inside the ergosphere, in a way that sends one piece falling into the black hole while the other piece escapes back out, carrying more energy than the original object had when it entered. This sounds like it violates conservation of energy, but it doesn't. The piece that falls into the black hole enters on a special trajectory that actually reduces the black hole's energy. It effectively carries negative energy into the event horizon, as measured by a distant observer. The black hole loses rotational energy. It slows down slightly, and that lost rotational energy is what gives the escaping piece its extra energy. You've essentially stolen energy from the black hole's spin and used it to boost the escaping fragment. This is the Penrose process, and while it's a theoretical mechanism that would be extraordinarily difficult to engineer in practice, it demonstrates something profound. A spinning black hole is not just a gravitational pit from which nothing returns. It is a reservoir of extractable energy. The rotation of space-time itself contains energy, and under the right conditions, that energy can be tapped. But nature has found a far more practical way to extract energy from a spinning black hole. In 1977, astrophysicists Roger Blanford and Roman Znarek proposed a mechanism that doesn't rely on cleverly aimed particles. Instead, it uses magnetic fields. When a spinning black hole sits at the center of an accretion disk, that disk is filled with electrically charged plasma, and plasma carries magnetic fields. Some of those magnetic field lines inevitably thread through the ergosphere. As the black hole spins and frame dragging twists the space-time around it, those magnetic field lines get twisted too. They wind up, coil, and tighten. The twisting of the field lines generates enormous electromagnetic energy, which is funneled outward along the black hole's rotational axis in the form of powerful jets, columns of energy and matter launched away from the black hole at nearly the speed of light. These jets can extend for thousands, sometimes millions of light years, into intergalactic space. The Blanford-Znarek mechanism is now widely believed to be the engine behind some of the most powerful phenomena in the universe. Active galactic nuclei, the brilliant cores of certain galaxies, are thought to be powered by supermassive black holes feeding on surrounding gas while simultaneously launching jets through this process. Quasars, the most luminous persistent objects in the known universe, visible across billions of light years, are believed to be powered by the same mechanism. A rapidly spinning supermassive black hole surrounded by a dense accretion disk, threading magnetic fields through its ergosphere and converting its rotational energy into twin beams of matter and radiation that outshine entire galaxies. The history behind this understanding is one of the most dramatic detective stories in all of astronomy. In the late 1950s and early 1960s, radio astronomers began cataloging mysterious point-like sources of radio emission scattered across the sky. When they turned optical telescopes to these positions, they found faint bluish objects that looked like stars, but their spectra were baffling. The patterns of light they emitted at different wavelengths didn't match any known type of star. The spectral lines were shifted so far toward the red end of the spectrum that they were initially unrecognizable. Astronomers called them quasi-stellar radio sources, later shortened to quasars, and for years they remained one of the deepest puzzles in astrophysics. In 1963, the Dutch-American astronomer Maarten Schmidt made the breakthrough. He was studying an object catalogued as 3C273, and he realized that its spectral lines were not exotic or unknown at all. They were ordinary hydrogen emission lines, but redshifted by an enormous amount. That redshift meant 3C273 was not a nearby star. It was an extragalactic object, billions of light years away. And if it was that far away, then its apparent brightness implied it was producing an almost inconceivable amount of energy. More than an entire galaxy containing hundreds of billions of stars, all pouring out of a region smaller than our solar system. Nothing in known physics could explain this. Nuclear fusion, the engine that powers every star in the universe, was hopelessly inadequate. Even if you somehow combined the output of every star in the Milky Way and concentrated it into one small volume, you still wouldn't match a quasar's sustained luminosity. The answer, pieced together over the following decades, was accretion onto a spinning supermassive black hole. Only the gravitational energy released by matter spiraling into a rapidly rotating black hole, amplified by the extraordinary efficiency that spin enables, could explain what astronomers were seeing. A supermassive black hole weighing 1 billion times the mass of our sun, spinning near the extremal limit, surrounded by a dense accretion disk and launching jets through the Blandford-Znajek mechanism, can produce luminosities of 10 trillion to 100 trillion times the luminosity of our sun. To put that in perspective, take every star in the Milky Way, all few hundred billion of them, and multiply their combined light by a factor of 1,000 or more. That is a single quasar. One object, powered by one spinning black hole, outshining its entire host galaxy 100-fold. These are not hypothetical objects confined to textbooks. They are observed in enormous numbers across the cosmos. The most distant quasars detected so far emitted their light when the universe was less than 1 billion years old, meaning we see them as they existed more than 12 billion years ago, already blazing at extraordinary luminosities. The fact that supermassive black holes were already spinning fast enough to power quasars that early in cosmic history tells us something profound about how quickly spin-up must have occurred in the young universe through rapid accretion and frequent mergers in the dense, chaotic conditions of the early cosmos. Quasars were far more common back then, when galaxies were forming rapidly and collisions between them were frequent, but they still exist today. Every quasar we observe, past or present, is direct evidence of what happens when a black hole spins fast enough. The spin enables the efficiency. And without that efficiency, the most luminous, persistent objects in the known universe simply could not exist. Without spin, these jets wouldn't exist. A non-spinning black hole has no ergosphere. There is no frame dragging to twist the magnetic field lines. The Blandford-Znajek mechanism requires spin. The faster the spin, the more powerful the jets. This is why understanding black hole spin matters not just as a theoretical curiosity, but as the key to understanding some of the most energetic phenomena in the cosmos. we don't have to take any of this on faith. Astronomers have developed techniques to actually measure how fast real black holes are spinning, and the results are remarkable. One of the most powerful methods is called X-ray reflection spectroscopy. When gas in an accretion disk spirals toward a black hole, it reaches temperatures of millions of degrees and emits X-rays. Some of those X-rays shine inward, hitting the inner parts of the accretion disk and bouncing off like light reflecting from a mirror. When those reflected X-rays reach our telescopes, they carry a fingerprint. Atoms of iron in the accretion disk produce a characteristic emission feature at a specific energy, around 6.4 kilo electron volts. In a laboratory, this feature would appear as a sharp, narrow spike at that precise energy. But near a black hole, the extreme gravity stretches and distorts this feature. Photons climbing out of the deep gravitational well lose energy, shifting their wavelength towards the red end of the spectrum. Photons emitted from parts of the disk moving towards us get boosted in energy. Photons from parts moving away get dimmed. The result is that the sharp laboratory spike gets smeared and skewed into a broad, lopsided shape. And the exact shape of that distortion depends on how close the inner edge of the accretion disk gets to the event horizon, which in turn depends on how fast the black hole is spinning. A slowly spinning black hole, whose innermost stable orbit sits far from the horizon, produces a moderately distorted iron line. A rapidly spinning black hole, whose innermost stable orbit sits much closer to the horizon, produces a dramatically stretched and skewed line. By carefully analyzing the shape of this spectral feature, astronomers can work backward and determine the spin. Using this technique and others, astronomers have measured the spins of dozens of black holes. Some are spinning slowly, but many are spinning fast, remarkably fast. Consider the story of how we came to know this. In 1964, instruments aboard a sounding rocket detected a powerful source of X-rays in the constellation Cygnus. It was designated Cygnus X1, the first X-ray source catalogued in that region of the sky. At the time, X-ray astronomy was in its infancy, and no one knew what this object was. Over the following years, astronomers identified its optical counterpart, a blue supergiant star roughly 7,000 light-years from Earth, called HDE 226,868. The X-rays were coming from something invisible orbiting that supergiant, something pulling gas away from the star's outer layers and heating that gas to millions of degrees as it spiraled inward. By the early 1970s, careful measurements of the supergiant's orbital motion revealed that the invisible companion had a mass far exceeding the limit for a neutron star, which tops out at about 2 to 3 solar masses. Whatever was orbiting that supergiant was far too heavy to be anything other than a black hole. Early estimates placed its mass at roughly 15 solar masses, but more precise measurements published decades later revised that figure upward to approximately 21 times the mass of our Sun, making it one of the heaviest stellar mass black holes known in our galaxy. The identification was so controversial at the time that it became the subject of a famous bet between Stephen Hawking and Kip Thorne. Hawking wagered that Cygnus X1 was not a black hole. Thorne wagered that it was. As the evidence mounted through the 1970s and 80s, the case became overwhelming, and Hawking conceded the bet in 1990, signing the concession statement with good humor. Cygnus X1 became one of the first objects widely accepted as a stellar mass black hole. And decades later, when X-ray reflection spectroscopy was applied to this system, it revealed something extraordinary. The black hole called Cygnus X1 has been measured with a spin parameter of approximately 0.97 or higher. That's 97% or more of the theoretical maximum. One of the first black holes humanity ever identified turned out to be one of the fastest spinning objects we've ever measured. Then there is GRS 1915 plus 105, discovered in 1992 as a bright X-ray source in the constellation Aquila. This system stunned the astronomical community in 1994 when observers detected blobs of material being ejected from it at apparent velocities exceeding the speed of light. At first glance, this seemed to violate everything physics says about the cosmic speed limit. But the apparent faster-than-light motion was an illusion, a well-understood geometric effect called superluminal motion. When jets of material travel at a large fraction of light speed and are aimed nearly toward the observer, the combination of the jet's high velocity and its small angle to our line of sight compresses the arrival times of successive light signals at our telescopes. The material appears to cross the sky faster than light, but its true velocity never exceeds it. The real speed of the jets was still extraordinary, roughly 92% of the speed of light. These were among the fastest outflows ever observed from a stellar mass black hole in our galaxy. The power required to launch material at such speeds pointed directly to a rapidly spinning black hole, driving the Blandford-Znarek mechanism at extreme efficiency. Subsequent spin measurements confirmed what the jets had already implied. GRS 1915 plus 105 harbors a black hole spinning at or very near the theoretical maximum. The jets were not merely impressive. They were visible, dramatic proof that rapid spin fundamentally changes what a black hole can do to the universe around it. These are not unusual. Among the black holes whose spins have been measured, a significant fraction are spinning at more than 90% of the theoretical limit. The universe appears to be remarkably good at creating rapidly spinning black holes through the combination of collapse, accretion, and mergers that we discussed earlier. Gravitational wave observations offer another window into black hole spin. When two black holes merge and LIGO detects the resulting gravitational waves, physicists can extract information about the spins of the original black holes and the spin of the final merged remnant from the signal. These measurements have confirmed that mergers can produce black holes with a wide range of spins, some moderate, some high, depending on the geometry of the collision. What all these observations tell us is that spin is not a rare or exotic property of black holes. It is the norm. Almost every black hole we've studied is spinning, many of them rapidly. And that means the phenomena we've discussed tonight, frame dragging, the ergosphere, the shrinking of the innermost stable orbit, the Penrose process, the Blandford-Znarek mechanism, the powering of jets and quasars, all of these are not theoretical possibilities. They are happening right now across the universe, around black holes spinning at extraordinary rates. But here's the question that all of this builds toward. If black holes accumulate angular momentum through accretion and mergers, and if many observed black holes are already spinning at more than 90% of the maximum, what happens as they approach 100%? What happens at the absolute edge? Because the Kerr solution tells us something deeply unsettling about that boundary. As the spin parameter approaches 1, the two horizons converge. The innermost stable orbit collapses toward the event horizon. The ergosphere grows larger. The frame dragging intensifies. Everything becomes more extreme, more violent, more warped, and at a spin parameter of exactly 1, the mathematics reaches a critical threshold, a boundary that changes the very nature of what a black hole is, what that boundary means, why the universe seems determined to prevent any black hole from reaching it, and what the mathematics predicts would happen if it was somehow crossed. That is what we need to explore next. We've seen what spin does to a black hole. We've watched space-time twist and drag. We've seen the event horizon shrink, the innermost stable orbit collapse inward, the ergosphere swell. We've seen how rapidly spinning black holes power jets that stretch across millions of light years and drive quasars that outshine entire galaxies. And we've established that many real black holes in the universe are already spinning at more than 90% of the theoretical maximum. But we haven't yet confronted the boundary itself. We haven't asked what happens when a black hole approaches the absolute ceiling. And more importantly, we haven't asked why the universe seems to resist letting any black hole actually reach it. The extremal Kerr limit. That's the technical name for the boundary. It's the point where the spin parameter equals exactly 1. And to understand what this means physically, we need to return to the geometry of the two horizons. Remember that a spinning black hole, described by the Kerr solution, has two horizons, an outer event horizon and an inner horizon. As the spin increases, these two surfaces move toward each other. The outer horizon shrinks inward. The inner horizon expands outward. They converge, slowly and steadily, as the spin parameter climbs from 0 toward 1. At low spins, the gap between them is wide. At moderate spins, it narrows. At high spins, they're close together. At a spin parameter of exactly 1, they meet. The two horizons merge into a single surface. This is the extremal Kerr black hole, and it represents a kind of knife edge. A black hole balanced precisely at the boundary between having a normal event horizon structure and having something else entirely. Below a spin of 1, the black hole has two distinct horizons separated by a gap, and the space-time between them, while exotic, is mathematically well defined. At a spin of exactly 1, the horizons merge. The gap collapses to 0. The geometry becomes degenerate in a mathematical sense. The properties of the space-time at this merged horizon are different from those of a sub-extremal black hole. The surface gravity at the horizon drops to 0. A freely falling object approaching the extremal horizon would experience diminishing tidal forces as it got close, at least along certain directions, in contrast to the violently increasing tides you'd feel approaching a non-spinning black hole. The entire character of the boundary changes, and beyond a spin of 1, the horizons don't just get closer, they vanish. They cease to exist. The mathematics of the Kerr solution with a spin parameter greater than 1 describes a space-time with no event horizon at all. The singularity sits exposed, naked, visible to the rest of the universe. But that is a discussion for later. Right now, we need to ask a more practical question. Can a black hole actually reach a spin of 1? Can it be spun up to the extremal limit? At first glance, it seems like the answer should be straightforward. If accretion adds angular momentum, and mergers add angular momentum, then just keep feeding the black hole. Keep adding spin. Eventually you'll push it all the way to 1. The spin parameter is just a number. Numbers can be increased. Why should there be any difficulty? The difficulty lies in a subtlety that most people overlook. When matter falls into a black hole, it doesn't only bring angular momentum, it also brings energy. And in general relativity, energy and mass are equivalent. Einstein's famous equation tells us that energy is mass multiplied by the speed of light squared. Every particle that falls into a black hole adds to its mass as well as to its angular momentum. And this is where the trap appears. The spin parameter is not just the angular momentum. It is the ratio of angular momentum to mass. More precisely, it's the angular momentum divided by the mass times a constant related to the speed of light and Newton's gravitational constant. So to increase the spin parameter, you can't just add angular momentum. You have to add angular momentum faster than you add mass. If you add both at the same rate, in the right proportions, the spin parameter stays the same. If you add more mass relative to angular momentum, the spin parameter actually decreases. The black hole gets heavier, but doesn't spin any faster. It effectively slows down in the dimensionless sense, even though it has more total angular momentum than before. Think of it this way. Imagine a merry-go-round in a playground. You're standing beside it, pushing the edge to make it spin faster. Each push adds rotational momentum. But now imagine that every time you push it, the merry-go-round also gets heavier. New weight is bolted on with each shove. If the weight added is proportional to the force of your push, the merry-go-round doesn't actually spin any faster. Your push adds rotation, but the extra weight adds resistance, and the two effects cancel out. To make it spin faster, you need to find a way to push without adding weight, or at least to push proportionally harder than the weight being added. Near a black hole, physics conspires to make exactly this increasingly difficult as the spin approaches the maximum. Here's why. As a black hole spins faster, its innermost stable circular orbit shrinks closer to the event horizon. We discussed this earlier. At low spins, the innermost stable orbit sits about 3 times the event horizon radius. At high spins, it moves much closer, and the location of this orbit determines the angular momentum and energy of the matter that falls in. Matter in an accretion disk spirals inward through a series of roughly circular orbits. At each orbit, friction and radiation remove a tiny amount of energy, causing the matter to drop to a slightly smaller orbit. This continues until the matter reaches the innermost stable orbit. At that point, there are no more stable circular paths. The matter plunges in, crossing the event horizon and adding its energy and angular momentum to the black hole. The ratio of angular momentum to energy that the infalling matter carries depends on which orbit it fell from. Matter, falling from the innermost stable orbit of a slowly spinning black hole, carries a certain ratio. Matter falling from the innermost stable orbit of a rapidly spinning black hole carries a different ratio. And here's the key point. As the spin increases and the innermost orbit moves closer to the horizon, the ratio of angular momentum to energy that each chunk of infalling matter delivers changes in a way that makes it harder and harder to increase the spin further. Each new bit of matter adds angular momentum, yes, but it also adds mass. And the mass contribution becomes increasingly significant relative to the angular momentum contribution as the spin climbs. The higher the spin already is, the less efficient each new chunk of matter becomes at pushing the spin even higher. It's like trying to fill a bathtub where the drain gets wider as the water gets deeper. At first, the water rises quickly, but the higher the water level gets, the faster it drains out. You're still pouring water in, but an increasing fraction is flowing out through the widening drain. In the black hole case, you're still adding angular momentum, but an increasing fraction of what you add goes into mass rather than spin, and the spin parameter rises more and more slowly. But this isn't even the full story. Because accretion doesn't just involve matter, it also involves radiation. And radiation is where nature's resistance becomes truly formidable. In 1974, the physicist Kip Thorne published a landmark analysis of this problem. Thorne asked a precise question. If a black hole is fed by a standard thin accretion disk, the kind of disk where gas spirals inward in a flat, pancake-like structure, radiating energy as it goes, how fast can the black hole ultimately spin? Thorne's analysis was meticulous. He didn't just track the matter falling into the black hole, he also tracked the radiation the disk emits. When matter spirals through an accretion disk, it gets hot, extremely hot. Temperatures in the inner regions of the disk can reach millions of degrees. At these temperatures, the gas radiates intensely, primarily in X-rays. This radiation shines in all directions. Some of it escapes outward, away from the black hole, and that's what our telescopes detect. But some of it shines inward, toward the event horizon. And some of that inward directed radiation gets captured by the black hole. Now, here's what makes this so consequential. Photons carry both energy and momentum in the direction they travel. And near a rapidly spinning black hole, the geometry of spacetime is highly asymmetric. The innermost stable orbit is very close to the event horizon, and the accretion disk in this region is orbiting at tremendous speed in the same direction as the black hole's spin. The photons emitted by this disk are emitted in all directions from the disk's perspective. But because the disk is moving so fast relative to a distant observer, the radiation is strongly beamed forward in the direction of the disk's orbital motion. Some of these photons escape to infinity. Some fall into the black hole. And crucially, the photons that the black hole preferentially captures are not the ones that would help it spin faster. Because of the extreme curvature of space-time near a rapidly spinning black hole, the photons most likely to be captured are the ones traveling on orbits that carry angular momentum opposite to the black hole's spin direction. These are photons on retrograde orbits, photons that effectively push against the rotation rather than with it. Think about what this means. The accretion disk is feeding the black hole matter that adds angular momentum in the spin direction. But the radiation from that same disk, when captured by the black hole, adds angular momentum in the opposite direction. The matter spins the black hole up. The captured radiation slows it down, and as the spin gets higher and higher, as the innermost stable orbit moves closer and closer to the horizon, the radiation effect becomes stronger and stronger relative to the matter effect. Thorne calculated the equilibrium. He found the spin value at which angular momentum added by infalling matter is exactly balanced by angular momentum subtracted by captured radiation. The answer was approximately 0.998, not 1, not the theoretical maximum, but 0.998, 99.8% of the maximum. This result, now known as the Thorne limit, was striking. It showed that a standard thin accretion disk cannot spin a black hole all the way to the extremal limit. Nature has a built-in brake. The very radiation produced by the accretion process itself fights against the spin-up. And the closer the black hole gets to the maximum, the harder that brake pushes. At 0.998, the system reaches a standoff. The matter keeps trying to spin the black hole faster. The captured radiation keeps pushing back. And the two effects balance perfectly, freezing the spin just below the theoretical ceiling. This is worth pausing to appreciate. There is no law of physics that simply decrees a black hole cannot spin faster than 0.998. There is no rule written into general relativity that sets this number as a hard limit. Instead, This limit emerges from the detailed interplay of matter, radiation, and curved spacetime. It is an emergent constraint arising from the physics of the accretion process itself rather than from any fundamental prohibition. The universe doesn't say, "You cannot spin faster." It says, "Every mechanism you use to try to spin faster will also produce effects that resist further spinning." But the Thorne limit is not the final word on the subject, and it's important to understand why. The Thorne limit of 0.998 applies specifically to one scenario: a black hole being fed by a geometrically thin, optically thick accretion disk in a steady state. This is the standard model of accretion called the Novikov-Thorne disk model. In this model, the disk is thin, flat, and extends down to the innermost stable circular orbit. The gas radiates efficiently, the disk shines brightly, and the captured photons create the braking effect that caps the spin. But real astrophysical situations are not always this clean. There are other ways to add angular momentum to a black hole, and those pathways are not necessarily subject to the same limit. Consider thick accretion disks. In some environments, the accretion flow is not thin and flat, but geometrically thick, puffed up by radiation pressure or magnetic fields. In a thick disk, the flow dynamics and radiation patterns differ. The photons captured by the black hole may carry different ratios of angular momentum. Some thick disk models allow slightly higher or lower equilibrium spins than the thin disk Thorne limit, depending on the detailed geometry and physics of the flow. Consider magnetized accretion. Real accretion disks are threaded by magnetic fields, and these fields can transport angular momentum in ways that a purely hydrodynamic analysis doesn't capture. Magnetic fields can connect different parts of the disk, transferring angular momentum from inner regions to outer regions. They can also connect the disk to the black hole itself through the ergosphere, extracting rotational energy from the black hole through the Blandford-Znah-Yek mechanism we discussed earlier. In strongly magnetized flows, the spin equilibrium can be different from the Thorne value. Some simulations of magnetically arrested disks, where magnetic fields build up near the event horizon until they become dynamically important, find equilibrium spins that are somewhat lower than 0.998, perhaps around 0.9 or 0.95, because the magnetic extraction of spin energy through jets is so efficient that it counteracts the spin-up from accreting matter. Consider mergers. When two black holes merge, the angular momentum of the final remnant is determined by the gravitational dynamics of the collision, not by any accretion process. There's no accretion disk involved, no captured photons, no Thorne limit. The final spin depends on the masses and spins of the two original black holes and the angular momentum of their orbit. In principle, a merger could produce a remnant with a spin parameter very close to 1, higher than the Thorne limit, because the physics governing the outcome is completely different. Numerical simulations of binary black hole mergers have shown that under certain configurations, the remnant spin can exceed 0.95, though reaching values extremely close to 1 requires very specific initial conditions. So the Thorne limit is not a universal law. It is a specific prediction for a specific scenario. The broader lesson is more nuanced. Different mechanisms of angular momentum delivery come with different natural brakes. Thin disk accretion has its captured photon brake. Magnetically dominated accretion has its jet-driven brake. Even mergers are subject to gravitational wave emission, which carries away angular momentum during the inspiral and plunge phases, preventing the remnant from acquiring all of the orbital angular momentum. Every pathway to higher spin encounters its own form of resistance. The details vary, the numbers differ, but the pattern is consistent. The universe makes it progressively harder to add the next increment of spin as the extremal limit approaches. Let's examine why this resistance stiffens so dramatically near the maximum. The answer lies in the behavior of the spacetime geometry itself as the spin parameter approaches 1. As the spin climbs toward the extremal value, the innermost stable circular orbit moves ever closer to the event horizon. At a spin of 0.9, it's already significantly closer than it would be for a non-spinning black hole. At 0.99, it's closer still. At 0.999, it's hugging the horizon. And the closer the innermost orbit gets to the horizon, the more extreme the conditions become in the region where matter makes its final plunge. In this region, time dilation becomes extraordinary. From the perspective of a distant observer, events near the horizon appear to slow down. Light emitted from the innermost orbit is massively redshifted, stretched to longer and longer wavelengths as it climbs out of the gravitational well, losing almost all its energy by the time it reaches a distant observer. This means the radiation we can detect from the innermost disk becomes increasingly faint, even as the disk itself, in its own local frame, is radiating furiously. Frame dragging near the horizon of a near extremal black hole is almost total. Space-time is being pulled along at nearly the speed of light. Everything in this region, matter, light, magnetic fields, is caught in a vortex so intense that the distinction between moving with the spin and moving against it becomes a distinction between vastly different physical experiences. Particles orbiting with the spin can survive in stable orbits very close to the horizon. Particles on retrograde orbits, moving against the spin, cannot get anywhere near as close. They are expelled outward by the extreme frame dragging, unable to penetrate deep into the spinning space-time. This asymmetry is part of what creates the Thorne break. Photons on retrograde trajectories, the ones carrying angular momentum opposite to the spin, are preferentially captured because they travel on orbits that dip closer to the horizon. But as the spin approaches 1, even these photons find it increasingly difficult to reach the horizon. The geometry of the near extremal spacetime creates an ever narrower window through which retrograde photons can be captured. Meanwhile, the conditions for adding prograde angular momentum through matter accretion also tighten. The energy cost of each additional increment of spin becomes larger and larger. Imagine pushing a heavy door that gets harder to push the wider it opens. At first, a gentle shove moves it significantly. Halfway open, you need a firm push. 3/4 open, you're leaning into it with all your weight, and those last few degrees require more effort than everything before combined. Spinning a black hole toward the extremal limit is like that. Getting from 50 to 90% of the maximum takes time, but it's straightforward. Getting from 90 to 99 takes significantly more. From 99 to 99.9 takes enormously more. And approaching 100% requires overcoming resistance that grows without bound. This is not a coincidence. It's a reflection of something deep in the mathematics of general relativity. The extremal Kerr solution, the black hole with a spin parameter of exactly 1, sits at a boundary in the space of possible solutions. On one side of this boundary are ordinary black holes with well-defined horizons. On the other side is something that might not be a black hole at all. The mathematical structure of general relativity seems to place this boundary at a kind of asymptotic limit, a value that can be approached ever more closely but never quite reached through any realistic physical process. And the resistance does not apply only to accretion disks. Physicists have explored other pathways. They've asked whether you could throw a single particle with precisely chosen properties into a near extremal black hole to push the spin past one. They've asked whether a carefully aimed beam of electromagnetic radiation could do the job. They've even asked whether the merger of two already rapidly spinning black holes could produce a remnant beyond the limit. In every case, the answer has been the same. The universe refuses. Every mechanism that adds angular momentum also adds mass or triggers radiation or encounters some other countervailing effect that prevents the spin from reaching one. The details of how each attempt fails are remarkable and reveal deep features of general relativity, and we'll explore them fully when we confront the question of whether any physical process anywhere in the cosmos has ever succeeded in pushing past the boundary. But the pattern is already clear. The closer the spin parameter gets to 1, the more efficiently physics resists the next increment. It is as though space-time itself has an immune response, growing more selective, more vigilant, the closer the boundary approaches. These results are not just isolated calculations, they form a consistent pattern across decades of research. Every physical process that has been examined, every thought experiment, every numerical simulation, every analytical calculation arrives at the same conclusion. You can get close, you can get very close, but you cannot reach one. The extremal limit acts like a mathematical asymptote, a value that the spin parameter approaches ever more slowly without ever arriving. And this brings us to the deepest question. What if it could be crossed? What if, somehow, some exotic process, some configuration of fields and matter that no one has yet imagined, managed to push a black hole's spin past the extremal limit? What would happen? What would the universe look like if the spin parameter exceeded 1? The answer, according to the Kerr solution, is extraordinary and disturbing. The event horizon would not merely shrink. It would not merely thin out or weaken. It would disappear entirely. The singularity, that point or ring of infinite density at the heart of the black hole, would be exposed to the rest of the universe, visible, accessible, no longer hidden behind any horizon. This possibility, called a naked singularity, raises some of the deepest questions in all of theoretical physics. Questions about predictability, about causality, about whether the universe can even function if singularities are allowed to exist without horizons to conceal them. Whether the universe permits such a thing, whether there is a fundamental law forbidding it, and what it would mean for our understanding of physics if naked singularities could exist. That is the final piece of this story. And it begins with a conjecture proposed by one of the greatest mathematical physicists of the 20th century, a conjecture that remains unproven to this day, and that strikes at the very heart of what we can and cannot know about the universe. We followed a black hole's spin from its birth in the collapsing core of a dying star, through the long, slow accumulation of angular momentum from accreting matter, through the violent instant of a merger, all the way up to the threshold where the spin parameter approaches 1. And we've seen how the universe fights back at every step, how captured radiation, energy costs, and the geometry of space-time itself conspire to resist further spin-up, creating ever steeper barriers as the extremal limit draws near. Every physical process that has been examined, from thin disk accretion to individual particle capture to electromagnetic radiation, runs into the same wall. You can approach the limit, you can get tantalizingly close, but the mathematics of general relativity and the physics of real accretion seem to prevent the black hole from actually crossing that final boundary. But what if it could be crossed? What would happen? What does the mathematics predict for a Kerr solution with a spin parameter greater than 1? The answer is both simple and terrifying. The event horizon vanishes, not thins, not weakens, not shrinks to a tiny size. It ceases to exist entirely. There is no event horizon at all. The mathematical solution for a Kerr spacetime with a spin parameter exceeding 1 describes a region of spacetime that contains a singularity, a point or ring where the curvature of spacetime becomes infinite, where densities reach infinity, where the known laws of physics break down completely. But that singularity is not hidden. It is not shielded from the rest of the universe by any horizon. It sits there, exposed, visible in principle to any observer anywhere in the universe who happens to look in its direction. This is what physicists call a naked singularity. And to understand why it is so deeply troubling, you need to understand what an event horizon actually does for the rest of the universe. The event horizon of a normal black hole is not just a boundary that traps light and matter. It is a shield. It protects the rest of the universe from the singularity within. The singularity is where physics breaks down. At the singularity, the curvature of spacetime becomes infinite. The equations of general relativity produce meaningless answers. Infinities that cannot be interpreted physically. The singularity is a point where our current understanding of physics fails completely. We don't know what happens there. We don't know what replaces the infinite densities and curvatures that the equations predict. We suspect that a complete theory of quantum gravity, a theory that merges general relativity with quantum mechanics, would resolve these infinities and replace them with something finite and understandable. But we don't have that theory yet. The singularity remains a blind spot in our understanding of the universe, and the event horizon keeps that blind spot hidden. Whatever bizarre, law-breaking physics occurs at the singularity, it stays behind the horizon. It cannot send signals to the outside universe. It cannot influence events beyond the event horizon. The rest of the universe is protected from the breakdown of physics that occurs at the singularity, because the horizon acts as a one-way membrane. Information flows in, but never out. The singularity can be as wild and unpredictable as it wants. But the outside universe remains orderly and predictable. Now, imagine removing that shield. Imagine a singularity with no horizon around it. A naked singularity, sitting in open space-time, connected to the rest of the universe by ordinary causal pathways. Light could leave the vicinity of the singularity and travel to distant observers. Signals could emerge from a region where the laws of physics break down and propagate outward to influence events in the normal, well-behaved universe. This would be catastrophic for the predictability that general relativity normally guarantees. In general relativity, if you know the state of a system at one moment in time, the equations tell you what happens next. The future is determined by the present. This determinism is one of the foundational principles of classical physics. Given complete information about the gravitational field and the matter distribution at one instant, Einstein's equations predict everything that will happen afterward. but a naked singularity would violate this. At the singularity, the equations break down. They don't predict anything. They produce infinities, which are not predictions. They are admissions of failure. If signals can emerge from the singularity and reach the rest of the universe, then the future of the universe becomes unpredictable. You could have complete knowledge of every particle, every field, every curvature of space-time in the entire universe outside the singularity, and you still couldn't predict what happens next, because the singularity could emit anything, any signal, any particle, any burst of radiation, at any time, with no governing law to constrain it. The singularity would be a source of pure unpredictability injected into an otherwise deterministic universe. It would be like a hole in the fabric of causality. Events could emerge from it without causes, without any connection to the prior state of the universe. The entire framework of physics, the idea that the future follows from the past, would break down in the vicinity of a naked singularity. This is why the prospect of naked singularities disturbed physicists so profoundly. And this is why, in 1969, Roger Penrose proposed one of the most famous conjectures in all of theoretical physics. Penrose had already proven in 1965 that singularities are inevitable in general relativity under certain conditions. His singularity theorems, which earned him a share of the Nobel Prize in Physics in 2020, showed that when enough matter is concentrated in a small enough region, the formation of a singularity is unavoidable. The laws of general relativity guarantee it. You cannot prevent the collapse from reaching infinite density within the framework of classical general relativity. The singularity is a prediction of the theory, not an artifact of oversimplified models. But Penrose went further. In 1969, he proposed that while singularities do form, nature always hides them behind event horizons. Every singularity that forms through a realistic physical process, Penrose argued, will be clothed in an event horizon, concealed from the rest of the universe. No naked singularity will ever form from the gravitational collapse of matter or from any other physically realistic process. The cosmic censor, as Penrose poetically put it, ensures that the breakdown of physics at singularities remains forever hidden from view. This is the cosmic censorship conjecture, and despite more than 5 decades of intense work by some of the most brilliant theoretical physicists in the world, it remains unproven. The conjecture actually comes in 2 forms. The weak cosmic censorship conjecture states that singularities formed by gravitational collapse are always hidden inside event horizons and cannot be seen by distant observers. The strong cosmic censorship conjecture goes further. It states that the singularity is not just hidden from distant observers, but that no observer, even one who falls into the black hole, can see the singularity before being destroyed by it. The strong version is actually about the nature of the inner horizon, the Cauchy horizon that we mentioned earlier. It claims that this inner horizon is unstable in realistic situations, meaning that any observer trying to cross it would be destroyed by an instability that converts the inner horizon into a singularity before they could pass through. Both forms of the conjecture remain open problems in mathematical physics. Neither has been proven in full generality. Neither has been definitively disproven. The cosmic censorship conjecture occupies a peculiar position in physics. Almost everyone believes it is probably true, but no one has been able to prove it rigorously. Why is it so hard to prove? Because general relativity is a mathematically complex theory. proving something about all possible solutions to Einstein's equations, showing that no physical process can ever produce a naked singularity, requires understanding the full space of solutions, including solutions describing extreme, violent, highly dynamical spacetimes like collapsing stars and merging black holes. The mathematics needed to handle these situations rigorously is at the frontier of what humans can currently do. But while a rigorous proof remains elusive, a massive body of evidence supports the conjecture. Let's look at what we know. First, no observation has ever revealed a naked singularity. Astronomers have observed stellar mass black holes in binary systems. They have observed supermassive black holes at the centers of galaxies. They have measured the spins of dozens of black holes through X-ray spectroscopy and gravitational wave observations. Every single one is consistent with a normal black hole possessing an event horizon and a spin parameter below 1. Not a single observation has produced evidence of a horizon-free singularity anywhere in the universe. The supermassive black hole at the center of our galaxy, Sagittarius A star, has been studied intensively. Stars have been tracked orbiting it for decades. The Event Horizon Telescope collaboration has now produced direct images of the immediate surroundings of two supermassive black holes, Sagittarius A star at the center of our galaxy, and the black hole in M87, whose mass is roughly 6.5 billion times the mass of our Sun. In both cases, the observations are fully consistent with Kerr black holes spinning below the extremal limit. There is no sign of anything beyond the standard picture. Astronomers have not just passively failed to find naked singularities, they have actively searched for them, and to search for something, you need to know what it would look like. Theoretical physicists have spent considerable effort working out the observational signatures a naked singularity would produce, and how those signatures would differ from those of a normal black hole. The differences turn out to be stark. A Kerr black hole casts a shadow. When light from background sources or from the glowing accretion disk passes near the event horizon, some of it gets captured. The photons that cross the horizon never return. The result is a dark silhouette, roughly circular, set against the bright emission of the surrounding gas. This shadow is a direct consequence of the event horizon's existence. Light that crosses that boundary is gone forever, creating a region of darkness that telescopes can image. A naked singularity would not cast the same shadow. Without an event horizon, there is no boundary trapping light. Photons could pass arbitrarily close to the singularity and, depending on the geometry, emerge on the other side or scatter outward in unexpected directions. Instead of a dark void at the center, theoretical models predict that a naked singularity might produce a brilliant point or a bright ring where extreme gravitational lensing focuses incoming light rather than absorbing it. The contrast with a normal black hole could not be more dramatic. One is defined by the darkness of what it hides. The other would be defined by the brightness of what it reveals. The Event Horizon Telescope, images of both Sagittarius A star and M87 show clear, unambiguous shadows. The dark central region, the bright asymmetric ring of emission surrounding it, the brightness variations caused by the relativistic motion of the accretion disk. Every feature in those images matches the predictions of the Kerr solution for a spinning black hole with a well-defined event horizon. None of them match the predictions for a naked singularity. If either of these objects lacked an event horizon, the images would look fundamentally different. The dark center would be replaced by a bright concentration. the surrounding emission pattern would have a different morphology. The images rule out naked singularities at these locations with high confidence. Beyond direct imaging, there are other signatures astronomers have examined. The accretion disk around a naked singularity would behave differently because there is no innermost stable circular orbit in the conventional sense. Matter could orbit at radii that would be forbidden around a normal black hole, altering the temperature profile and luminosity of the disk. The X-ray spectrum would show emission features at different energies and with different line profiles than those observed from known black hole candidates. Every X-ray spectrum that has been carefully analyzed from a candidate system is consistent with the presence of a normal event horizon, and inconsistent with the theoretical predictions for a horizon-free singularity. Gravitational lensing patterns would also differ. A naked singularity bends light in ways subtly but measurably distinct from a black hole of the same mass and spin. These differences have been modeled in detail and compared against observations. No deviation from the standard Kerr prediction has been found. The observational verdict, while not absolutely final, is clear. Every tool we possess for probing the regions near compact objects, imaging, spectroscopy, lensing, gravitational waves, produces results consistent with black holes that have event horizons and spin parameters below the extremal limit. No credible evidence for a naked singularity has ever been found anywhere in the observable universe. LIGO's gravitational wave observations tell the same story. When two black holes merge, the gravitational wave signal encodes information about the masses and spins of the original black holes and the mass and spin of the final remnant. In every merger observed so far, the final remnant is consistent with a Kerr black hole below the extremal spin limit. The most famous detection, the event designated GBU1 50914, produced a remnant spinning at roughly 67% of the maximum. Other mergers have produced higher spins, but none have approached or exceeded the boundary. Second, every theoretical attempt to overspin a black hole has failed. Physicists have spent decades devising increasingly clever thought experiments designed to push a black hole past the extremal limit, and every single one has been defeated by some mechanism within general relativity. The most straightforward approach, as we discussed, is accretion. But accretion encounters the Thorne limit. Captured radiation creates a break that stores the spin below the maximum. Even modifying the geometry of the accretion flow doesn't help. Different disk models produce different equilibrium spins, but none exceed 1. A more creative approach was proposed by the physicist Robert Wald in 1974. Wald asked what happens if you try to throw a single test particle into a near-extremal Kerr black hole, choosing the particle's energy and angular momentum to be precisely the combination needed to push the spin past 1. Wald showed that if you choose a particle with enough angular momentum to overspin the black hole, that particle also has too much angular momentum to be captured. The black hole's gravitational field deflects it. It scatters off the effective potential barrier surrounding the black hole and escapes back to infinity. The very properties that would make the particle useful for overspinning the black hole are the same properties that prevent it from getting in. Later researchers refined this analysis. They considered particles with electric charge as well as angular momentum. They considered spinning test bodies rather than point particles. They considered quantum mechanical effects. In every case, when the analysis was done carefully, the black hole resisted. Some attempts initially appeared to succeed at the level of approximate calculations, but when higher order effects were included, the back reaction of the particle's own gravitational field on the spacetime, or the radiation emitted by the particle as it spirals in, those effects always prove sufficient to prevent the spin from exceeding 1. Some of the most compelling evidence comes from numerical relativity simulations. These are computer simulations that solve Einstein's full, non-linear field equations without approximation. They can model the merger of two black holes, the collapse of a rotating star, or the accretion of matter onto a spinning black hole with extraordinary precision. In every simulation that has been run, the result is a black hole with a spin parameter below 1. The simulations show the same pattern we've described. The spin climbs toward the limit, but is always prevented from reaching it by some combination of gravitational radiation, energy requirements, and the geometry of the near extremal spacetime. Third, there are theoretical arguments, not quite proofs, but strong suggestive reasoning, that connect cosmic censorship to deep principles of physics. One line of argument connects it to the second law of thermodynamics. Black holes have entropy, and the entropy of a black hole is proportional to the area of its event horizon. In the early 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes obey thermodynamic laws analogous to the laws governing heat engines and refrigerators. The area of the event horizon can never decrease in classical general relativity, just as entropy can never decrease in thermodynamics. Now consider the implications for overspinning. In any real physical process that spins a black hole up, accretion or a merger also adds mass. The area theorem is never violated because the added mass more than compensates for the effect of added spin. The total horizon area increases or stays the same throughout the process, consistent with the second law. But here is the critical point. If you could somehow push the spin parameter past 1, the event horizon would not merely shrink, it would vanish entirely. The area would drop discontinuously from a finite value to 0. The black hole's entropy, which is proportional to that area, would be destroyed in an instant. This would represent a catastrophic violation of the second law of black hole thermodynamics, one of the most fundamental principles connecting gravity to the rest of physics. The deep link between cosmic censorship and thermodynamics suggests that the universe may forbid naked singularities for the same reason it forbids entropy from decreasing. Not as an incidental consequence, but as a reflection of something fundamental about the structure of physical law. Another line of argument connects cosmic censorship to the stability of spacetime itself. The mathematician and physicist Demetrios Christodoulou has done extensive work on the mathematical structure of gravitational collapse. His results suggest that the formation of naked singularities in spherically symmetric collapse requires extremely fine-tuned initial conditions so precise that any tiny perturbation would cause an event horizon to form instead. In other words, even in cases where a naked singularity is mathematically possible, it is unstable. The slightest deviation from perfect symmetry or perfect tuning causes the collapse to produce a normal black hole rather than a naked singularity. If true, this would mean that naked singularities, even if they are technically allowed by the equations, would never form in the messy, imprecise, perturbed real universe. Despite all this evidence, the cosmic censorship conjecture remains precisely that, a conjecture. It has not been proven as a mathematical theorem, and there are reasons for caution. Some researchers have found solutions to Einstein's equations in higher dimensional spacetimes, where cosmic censorship appears to be violated. In 5-dimensional general relativity, for example, certain types of rotating black objects can become unstable in ways that might expose their singularities. These results don't directly apply to our 4-dimensional universe, but they show that cosmic censorship is not an automatic consequence of general relativity in all its possible forms. It might be a special feature of 4 dimensions, something that works in our universe but not in all mathematically consistent ones. Other researchers have found that in classical general relativity coupled to certain exotic forms of matter, naked singularities can form from generic initial conditions. These matter fields may not exist in nature, but their mathematical consistency shows that cosmic censorship depends on assumptions about what kinds of matter the universe contains, not just on Einstein's equations themselves. And then there is the deepest uncertainty of all. We don't know what happens at a singularity because we don't have a theory of quantum gravity. General relativity predicts that singularities have infinite density and infinite curvature, but most physicists believe these infinities are artifacts of applying a classical theory beyond its domain of validity. At the Planck scale, roughly 10 to the minus 35 meters, quantum effects should become dominant. General relativity should be replaced by a quantum theory of gravity that resolves the singularity into something finite and well-defined. If singularities are resolved by quantum gravity, the entire question of cosmic censorship might be transformed. Perhaps there is no true singularity to be naked. Perhaps what general relativity describes as a singularity is actually a region of extreme but finite curvature governed by quantum gravitational physics we don't yet understand. The question of whether an event horizon conceals the singularity becomes the question of whether it conceals the region of Planck scale physics. And that might have a different answer from the classical question. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that singularities are resolved in some way. But none of these theories is complete enough to definitively answer the cosmic censorship question. We are left in a state of educated ignorance, confident that the classical picture is incomplete, but unable to say exactly how it should be corrected. So, where does this leave us? What do we actually know about how fast a black hole can spin? We know that black holes acquire angular momentum through 3 main pathways: collapse, accretion, and mergers. Each of these pathways has its own dynamics, its own limitations, its own natural brakes that resist pushing the spin past the extremal boundary. We know that the Kerr solution in general relativity describes a rotating black hole with a spin parameter between 0 and 1. Below 1, the solution describes a normal black hole with an event horizon and a hidden singularity. At exactly 1, the 2 horizons merge. Above 1, the event horizon disappears and the singularity is exposed. We know that every physical mechanism examined, from prolonged thin disk accretion to single particle capture to electromagnetic radiation to black hole mergers, encounters resistance that intensifies as the spin approaches the extremal value. The Thorne limit of approximately 0.998 applies to one specific accretion scenario, but reflects a broader pattern. Nature fights back, and the fight gets harder the closer you get to the edge. We know that no observation has ever revealed a naked singularity or a black hole spinning faster than the extremal limit. Every measured spin is consistent with a Kerr black hole below the maximum. We know that the cosmic censorship conjecture, the proposal that physics always prevents naked singularities from forming, is widely believed, but remains unproven after more than 50 years of intense effort. And we know that the full answer almost certainly requires a theory of quantum gravity that we do not yet possess. The singularities at the hearts of black holes are not well described by general relativity alone. Whatever replaces the infinite densities and curvatures that the classical theory predicts might change the entire framework within which we ask these questions. But there is one thing we can say with confidence, and it brings us back to where we started. When we ask what happens when a black hole spins too fast, the answer is not what most people would expect. The phrase "too fast" doesn't mean the edge of the black hole exceeds some ordinary velocity. The event horizon is not a surface whipping through space like the rim of a spinning wheel. There is no surface. There is no edge. There is no material object whose speed could be measured in miles per hour or kilometers per second. What too fast means is something far more profound. It means the geometry of space-time itself approaches a limit beyond which the familiar structure of a black hole, the two horizons, the hidden singularity, the one-way membrane that shields the universe from the breakdown of physics at the center, would cease to exist. Too fast is not a mechanical limit. It is a geometric limit, a limit on the shape of space-time itself. And the universe, through a remarkable conspiracy of physical effects, appears to enforce that limit with extraordinary vigilance. Every mechanism that adds angular momentum to a black hole also triggers counter-mechanisms that resist the spin-up. Captured radiation pushes back. Energy costs escalate. The geometry of near-extremal space-time rejects the very particles that would push it over the edge. The closer a black hole gets to the boundary, the harder the universe works to keep it from crossing. Whether this resistance constitutes a fundamental law of nature, a deep consequence of quantum gravity, or something else entirely remains one of the great open questions in physics. The cosmic censorship conjecture, proposed over 50 years ago, still awaits its proof, or its disproof. The full theory of quantum gravity, which might resolve the question once and for all, remains one of the greatest unsolved challenges in science. But the picture that emerges from everything we've explored tonight is striking. A black hole spin is not a simple property like the spin of a top. It is a measure of how severely space-time is twisted, how dramatically the geometry of the universe is distorted near the black hole. And that geometry has a boundary, a limit written into the mathematics of general relativity itself. A boundary that separates ordinary black holes from something the universe may never allow. A spinning black hole approaches that boundary asymptotically, drawing ever closer but never arriving, like a traveler walking toward a horizon that recedes with every step. The universe appears to have rules about what it will and will not reveal. The singularity, the place where our understanding of physics breaks down, is kept hidden. The event horizon, that invisible boundary between the knowable and the unknowable, is maintained even as the black hole spins faster and faster, even as the space-time around it twists into a vortex that defies everyday intuition. The faster the spin, the more extreme the phenomena. Frame dragging intensifies, the ergosphere swells, the innermost stable orbit collapses, energy extraction becomes more efficient, jets grow more powerful, the geometry of space-time becomes more exotic, but through it all, The horizon holds. The singularity stays hidden. The universe remains predictable. Whether this will always be true, whether some exotic process in some extreme corner of the cosmos might one day challenge the cosmic censor, whether quantum gravity will reveal new physics that changes the question entirely. These remain mysteries, but they are mysteries of the best kind. The kind that reveal how much we have yet to learn about the universe we live in, about the nature of gravity and space-time, about the deepest structures of reality itself. When you look up at the night sky tonight and think about the black holes lurking at the centers of distant galaxies, the ones powering quasars that outshine 1 trillion suns, the ones launching jets that stretch across millions of light years, the ones spinning at 90 or 95 or 99% of the maximum, remember what you've learned. Those black holes are not just objects. They are boundaries. They mark the places where space-time curves so severely that the universe draws a line and says no further. They are spinning vortices in the fabric of reality, approaching a limit they can never quite reach. And in that eternal approach, in that endless, almost but not quite, lies one of the most beautiful and unsettling truths in all of physics. There are things the universe appears determined to keep hidden, even from itself. The fact that a 50-year-old conjecture, still unproven, still debated, still resistant to the most powerful mathematical techniques developed by multiple generations of physicists, sits at the very foundation of our understanding of gravity should give us pause. Cosmic censorship is not a minor technical detail or an obscure footnote in a textbook. It is the statement that the universe is predictable. That causality holds everywhere, at every moment, without exception. That the laws of physics, whatever they ultimately turn out to be, do not permit the kind of breakdown that a naked singularity would represent. If cosmic censorship is true, then there is a deep and beautiful principle at work. A principle that says the universe protects itself from its own most extreme possibilities. It bends, it warps, it twists space-time to astonishing degrees, but it does not allow the fabric to tear open and expose what lies behind it. And yet, we cannot prove it. We believe it. We have enormous evidence supporting it. Every observation, every simulation, every thought experiment constructed over 5 decades points in the same direction. But the rigorous mathematical proof that would elevate cosmic censorship from conjecture to theorem remains beyond our current reach. This is humbling. It means there are truths about the universe that we can see reflected in every piece of data we collect. Truths we feel intuitively must hold, but truths we cannot yet demonstrate with the certainty that mathematics demands. Think about what this reveals about our relationship with the cosmos. We have built telescopes that image the shadows of black holes across billions of light years. We have built detectors that measure ripples in space-time from collisions that happened before Earth existed. We have developed mathematical frameworks describing the geometry of the universe with extraordinary precision. And yet, one of the most fundamental questions about black holes, whether the universe truly forbids the exposure of singularities under all circumstances, remains open. The question is simple enough for a child to ask, and too hard for the greatest minds alive to answer definitively. This is not a failure of science. It is the honest frontier of knowledge, the boundary between what we understand and what we have yet to discover. Every great question that has ever been answered in the history of physics was once an open problem, A mystery that seemed intractable until someone found the right insight, the right framework, the right way of seeing that made the answer clear. Cosmic censorship may be proven tomorrow, or it may take another 50 years, or it may require a complete theory of quantum gravity, a theory that unifies general relativity and quantum mechanics and reshapes our understanding of spacetime at the most fundamental level. We simply do not know. And that uncertainty, far from being discouraging, is part of what makes this one of the most compelling stories in all of science. What we do know is breathtaking enough. Black holes spin. They carry angular momentum woven into the twisted geometry of spacetime itself. That spin reshapes everything around them, dragging space, warping horizons, powering jets that stretch across the cosmos. And that spin has a limit. Not a limit on any material surface. Not a speed that some physical edge mustn't exceed. But a limit on the geometry itself. A boundary in the mathematics of reality beyond which the familiar structure of a black hole, the event horizon that shields the universe from the unknown, would cease to exist. The universe approaches that boundary, it presses against it, but every mechanism available, every physical process we've examined, works to keep it from crossing. The cosmos permits extraordinary extremes, but it appears to draw one final non-negotiable line. And on our side of that line, the side where physics still works, where the future still follows from the past, where the fabric of space-time holds together no matter how violently it is twisted, we remain, watching, wondering, and still searching for the proof.